class, we only can do about 24 people in a room. And usually when we get the computers from the National Training Center, we can only get so many computers. All right, so welcome to the Stochastic Empirical Loading and Dilution Model, SELDM course. We're doing this by webinar today. Oh, actually, Dan, did I warn you that we're starting?
Yeah, I'm on it. I got it.
All right, you want me to start over?
No, you're good. I've been recording.
Okay. So I wanted to let everybody know that this training is sponsored by the Federal Highway Administration, Office of Program Development and Environmental Review. Susan Jones, who's on the call today, is our champion there, and she's been a great supporter for SELDM and getting everyone trained to use it. Thank you, Susan. So what we're trying to get at in this class and today is we want people to know that SELDM and the Highway Runoff Database exist and they're available for your use. We want to cover what SELDM is and what it does, and we'll see how easy it is to use the tools and learn how to find out more about them if you want to dive deeper. One of my lame dad jokes is that if you can do online shopping, you can use SELDM. And hopefully you'll agree with me by the end of today. So SELDM was developed by the USGS in cooperation with the Federal Highway as part of our overlapping missions. So we both kind of have the mission to provide tools, techniques, and information to do environmental studies. And SELDM is part of that vision for both agencies. So SELDM was initially designed for the NEPA process. So if you, as a DOT, wants to do something, let's say add a lane or something like that, there's this coordination and analysis. So the big question is, how will this site impact or affect the receiving water body? So when you ask that question, there's three possible answers. It's no, which is a finding of no significant impact. Yes, then you need to do an environmental impact statement, and then unknown. And very often the answer is unknown. So in that case, you want to do an assessment and try and get more information. So SELDM is very useful in all three of these. Is it can show that, you know, the risk of occurrence is very low, and so perhaps this site is not a high priority. If it's unknown, it can let you know which data might be more important to get. And if there's an impact, we can say, well, if we add this type of BMP or that type of BMP, how does that reduce the chances of having an impact? So for example, Susan and I worked on the Iliana project out in Illinois and Indiana, and there was this bridge that they were replacing. And the upstream watershed was like 3,000 square miles that had a bunch of cities and whatnot in it. So, in that case, we could pretty clearly show that replacing this bridge on a 3,000 square mile basin wasn't really going to have much of an effect at that place. So that's an extreme case. So, as you get down to smaller watersheds and different conditions, then, the answer might be different. And that's what SELDM is going to help tell you. So Federal Highway and we developed SELDM, and we wanted it to be a tool that was useful for the DOTs and environmental regulators. And to be useful, it had to be accepted. So we really got EPA, Fish and Wildlife Service, and Massachusetts Department of Environmental Protection on board to give us feedback to make sure it will be useful, right? If we have a model and people don't accept the results, then it's not useful. We also wanted it to be useful for DOTs to use, so we got a lot of people from state DOTs involved to make sure that the model was easy to use and that it had the information that DOTs would need. So to date, SELDM has been presented in 10 in-person classes and I think 3 webinar classes. And we know about use in 15 states, and we are, and I've kind of heard rumors of that it's being used elsewhere, but I haven't had contact with some of those people directly. So Seldom was designed as a highway model, but it can be used for other developed land covers. So very often we worry about a highway site, but regulators, highway people can also use Seldom to look at other contributors, or even if there's not a highway involved, people can look at the potential effects of urban runoff. So you could do that because Seldom is what's called a lump parameter model. That means we're not trying to like route pipes like you might do in SWIM. We just have an upstream basin and a site with like area, imperviousness, and other basin characteristics, which we'll see today. So with Seldom, we're not trying to do this just complex distributed watershed model. So for a highway, we would take all the highway that's contributing, and as you can see in this diagram, we put the highway down at the mouth of this upstream basin. And if there are urban areas, we can lump those urban areas to get the total area and simulate it as it's one discharge down here. Now that's an approximation, but once you dig into things, you can see that unless you have data at its site, an approximation, a good approximation is a lot better than some of a detailed watershed model that's built without calibration. All right, Seldom's also been used for TMDLs, total maximum daily loads. This pie chart is an example. We use Seldom with different imperviousness areas in the Willamette Basin in Oregon in cooperation with the Oregon DOT. And we were looking at total phosphorus loads. What's the state highways portion? What do they own as the stormwater phosphorus inputs? Now that doesn't include like wastewater treatment plants. So in the Willamette Basin, we found that agriculture was about 50% of the load. Developed areas were about 30% of the load. State highways were only about 2.5% of the loads. And even the forest greatly overshadowed the effects of the highways in the Willamette Basin. Even though forest loads are very small, like an order of magnitude less than highways, a large part of that basin is, contributing forest area. What this study also showed was that, if you took out the state highways completely, like went out and dug them up and, re-landscaped the area, that would make a very small difference on total phosphorus. So the state highway agency out there could not make a huge difference just because of the, how much discharge they had. But very minor improvements in agricultural practices could make a big difference because they're like half the load in the watershed. And, regular or more widespread BMP implementation by, in developed areas by municipalities or whatnot could make a big difference because, they owned a lot of the total load in that basin. All right, Seldom is also recommended, the recommended method in the NCHRP report 918, approaches for determining and complying with TMDL requirements related to roadway stormwater runoff. So this is a report by the National Academies of Science, Engineering, and Medicine. So the NCHRP is the National Cooperative Highway Research Program, which is a part of the National Academies. So we're pretty happy that they picked Seldom as, their method for looking at highway and urban runoff. So about this course, we'll be using a blended learning. So this class is like a beta test, or maybe it's what comes after a beta test. We don't want to use too many of these Greek letters nowadays, but so we're looking at periodic webinars. Usually our in-person course is 3 days, about 20 to 24 hours. We're doing 3 webinars of 2 hours just to kind of give you the overview. So hopefully you'll trust me, believe in me. So we're not going to cover all the detailed theory behind Seldom, but if you're the type of person that really wants to dig deep, or you want to be a Seldom modeler and be able to defend every choice, to the nth degree, Our YouTube videos cover a lot of the stuff that we covered in the in-person class. So they'll be available to you to either watch between classes or, even for the foreseeable future. Class materials, typically we hand it out like a CD-ROM. I'll load up some more zip files for people to download as the class goes on. But I already put Seldom, the highway runoff database, and some background reference material, which we can talk about. With 3 days at a couple hours each, we may not be able to dig too deep into using the models, but if people are highly interested and they want to have like small group teams to work together, or even if you're, a DOT person that's going to dive into using Seldom, very often Federal Highway has provided time for me to work with state DOTs to help people with questions and, get over any modeling hurdles. So if you're using Seldom after this class or even during it, I'm very happy to work together with you to help you get to the point where you can confidently use it and defend your results. Homework, probably about 80% of the people that attend the classes don't intend on becoming an expert modeler. They just need information to evaluate the results and, kind of get an idea of why and how. So I'm not going to assign homework, but again, the webinar, the videos are there for you. And we are very open to suggestions. So during or after this, if you can figure out, if you have good suggestions, or I guess any suggestions, I'll take. Good suggestions, I'll write down and implement. So, so that's kind of the overview of the class. I lament not having in-person classes now, because when you go away for a training course, you can focus on all that and kind of deep dive into it for 3 days. I know when we have webinars, people have coworkers, or now we have family members sometimes knocking on our door. So we lament the fact that we can get people together. Also, with an in-person class, it can be more fun and there's more synergy. So we will be having in-person classes in the future. So just because you take this webinar doesn't mean we won't be happy to see you in class at some point. I've also, when we've had the in-class sessions, people make cross connections between states. I would suggest, like, if you have an opportunity to participate in the virtual practitioners meeting coming up or the in-person practitioners meeting, they are very valuable. And a lot of that's because of the collaboration and the contacts that can be made. And I can give you more information, or Susan can give you more information about that meeting. I think Federal Highways is sponsoring one DOT person from each state to go to this, but other state DOT people are invited if the state will sponsor their beyond the one person. YouTube will be the primary platform if you want to become a Seldom expert. There's about 2.36 hours that I would call quote unquote mandatory if you want to be a Seldom expert / nerd. There's another about 2.63 hours recommended. And well, this slide could be updated. There's more new stuff. For example, if you're interested in using StreamStats, we've got a tutorial on how to use that, and we had a recent webinar on what different state DOTs are doing, and a new urban stormwater application in the Mystic River in near Boston, and how StreamStats can provide information for water quality analyses. If you go to the YouTube site, each video has an explanation. So, for example, this is how to use StreamStats, and we can see that there's a little explanation that says what this training module, and you can click see more, and you'll get all the information. I tried to put in related references, so if you really wanted to do a deep dive, it gives you all the background information. I guess the YouTube algorithm, you always hear the YouTube people say, you know, click, subscribe, watch, or whatever. So yeah, if you're more than welcome to. There may be your work email may not be able to do it, but you know you can subscribe, and then you'll get notifications. You know when new videos or webinars get posted online. Um, as one of the biggest tools available is the Seldom webpage. It lists all the Seldom reports that have come out in cooperation with state DOTs, in cooperation with Federal Highway Administration. The link is www.usgs.gov/Seldom. It also has links to as we update the software. And again, you know, it's a running archive of everything that's available. USGS has the publications warehouse. So these reports, or at least the USGS reports, in theory, will be available for the foreseeable future. I think we have reports back to 1849 on them. And on the Pubs warehouse, there's a lot of other valuable things, you know, for state DOTs, people and regulators. For example, all the flood frequency studies that we've done. All right, I think that covers our web page. And so again, as I kind of alluded to, this class, it's kind of an introduction to Seldom, and we'll play with Seldom, but you can decide how involved you may want to be. You can kind of get a general feel by watching the videos, or you know, just attending this class and playing with Seldom. Or you know, if you want to be an expert Seldom modeler, you could be more active, you know, read more reports, watch more videos. And, you know, as I said, if you slash your DOT, or, you know, your regulatory agency want to dive into Seldom and use it, I'm available for regular consultation to, you know, I can't do all your work for you, but I can definitely get you over the hump and, you know, talk about individual things, you know, as you cross each bridge. So that's another bad pun, right? All right. So that's an overview of the class. I think we'll just jump into a very high-level overview of Seldom, and then hopefully folks were able to download their Seldom copies so you can kind of play along as we click through the interface and and you know, and try to see how easy it is to use. If you haven't been able to download it, or you know your computer restrictions are so tight that you can't run a database application, which you know if you have Microsoft Access you should be able to. That's great to click along. If you don't, you can still get a very good feel for it by you know, just watching what we're doing here. All right, let me bring up the overview. And okay, as I mentioned, Seldom is the stochastic empirical loading and dilution model. And my dad joke for Seldom is that Seldom is the frequency we want to see water quality problems in our state, right? So Seldom provides concentrations, flows, and loads for stream quality analysis, and annual concentrations, flows, and loads for TMDLs, or lake quality analysis. Seldom was published by USGS in cooperation with the Federal Highway Administration. It's published as a USGS Techniques and Methods report, which means it's now an officially sanctioned USGS model. So this training module has about 26 slides and will take about a half hour, and then we'll hopefully have enough information to kind of jump in and use Seldom. And we won't be experts, but we'll know what we're doing as we go through. All right, I already mentioned that we developed and tested Seldom with regulatory agencies and a bunch of people from different DOTs. Okay, what is Seldom? So Seldom is stochastic because it uses Monte Carlo methods to create a sample of events representing the combinations of flows, loads, and concentrations that could occur over a long period of time. It's empirical because it's based on data and statistics rather than pure theory. For example, some models use like Stokes' law settling to try and see how a BMP works. What Seldom does is it uses actual statistics from the BMP database. So the answers you get from Seldom are based on actual data that was collected versus kind of theory. And just, casting this out is that, research has shown that Stokes' law falls apart for most sediment and solids that we worry about in highway and urban runoff. And, there's so much variation in grain size distributions from storm to storm that, some of these very complex models really don't do a good job at figuring out what's going on out there. Now, Seldom is a loading model. It provides storm and annual loads. So the storm loads help calculate that mass balance, and the annual loads are useful for the TMDL analysis. So it's a dilution model. So it does mixing of upstream and highway or urban runoff and indicates the chance of exceeding a target value downstream of the outfall. So as I mentioned, Seldom uses a simple mass balance approach to calculate the flows, concentrations, and loads by storm and by year. So what we have an upstream load, and the upstream load is a product of the concentration and storm flow. We have a highway runoff load or urban runoff load or BMP discharge load. And again, that's a concentration times the storm flow. So we add the two loads together to get the downstream load. We add the two storm flows together to get the downstream storm flow. When you divide the load by the downstream storm flow, you get that downstream concentration. So it's a very simple mass balance approach, but what we're doing is we use those Monte Carlo methods to create all those combinations of different environmental conditions that cause the variations that we see over a long period of time. Okay, Seldom is designed to facilitate scenario tests and sensitivity analysis. So scenario tests could be like, what is my highway doing today? And what would happen if I add one lane going in each direction? What's that additional area going to do to this receiving water? A sensitivity analysis is I only have so much money to collect data or so much time. What variables are most important to get me the best answer possible? So Seldom's designed to have projects. Now a project can be an actual, like I'm going to add a lane to I-84 in Tallinn, Connecticut, or project can be, or you could think of a project as just like a drawer in a filing cabinet that contains related information. Now in Seldom we do analyses. So an analysis is like a folder in that drawer that contains all the information that you used to get an answer. So there's description, the site information, upstream, your ecoregion, your precipitation, storm flow, runoff, and BMP. So each analysis can have one-to-many constituents. So, Seldom right now has a list of like 7,000 different stormwater constituents. In one analysis, you could run nutrients, organics, metals, everything. When we recently completed a TMDL study for the state of California, Caltrans, the California DOT, and I think we did it was either 51 or 53 constituents of concern for them for different TMDLs. Okay, Seldom was designed to support the environmental decision-making process. So when you go to a site, very few sites have actual data for that site. So we want to come in and we look at it and we want to do a first level analysis where we use like regional inputs. We might use ecoregion stream flow, ecoregion precipitation, ecoregion water quality. So we kind of very quickly, and that's what we'll do today, we'll just kind of use available information and very quickly we can get idea If there's a very remote chance of having an adverse effect, in which case perhaps we can say, okay, we're okay here, let's go focus on other sites where maybe we can do some more good. The second level analysis would be if there is some appreciable risk for potentially an adverse effect, where we might want to use more detailed data from nearby sites. So we try and use what's called hydrologic similarity to pick it. You want to pick a site that's very much like your site. Now, Seldom makes it easy to do this. It's almost as easy as doing a level 1 analysis, but you need to know a little bit more about the area and the surrounding sites to, pick which ones are best. Now, the final thing would be a third level analysis. So that's where you would use user-defined statistics from data collected potentially either very near your site or on site. Well, what's the problem with that? It's very expensive to collect data. It could take a year or several years to collect data. If you just ran out and collected a couple samples, they could be very misleading, and we'll talk about that later. So there could be delays of 1 or more years of data collection. And, if you look at a highway crosses many tributaries and many streams, there just aren't the resources out there to collect data at every site. So yes, and sometimes a very little data at a certain site may be worse than a lot of data collected over time, because it may give you a false impression of what you know. So Seldom, again, it's a mass balance model. It generates precipitation events, pre-storm flows, and runoff coefficients. So this is a little schematic diagram that'll give you the basic idea of the hydrology in Seldom. So Seldom is a runoff model. So first we have these storm event statistics. We use the EPA definition of a runoff generating event, and we use about 30 or 40 years of data from long-term NOAA stations across the country. So we get these statistics, and that Monte Carlo engine in Seldom generates, in New England, it's usually about 29 to 30 years of storms, about 1,500 to maybe 1,800 events. So we can use those events to say, well, what are the long-term risks of something going on? So we apply those precipitation events to the upstream basin and the highway site. So the highway site, usually it's highly impervious. So based on the imperviousness, we have runoff coefficients. So the precipitation times the runoff coefficient gives us our highway flow component. Now, when we look at the upstream basin, we have 2 storm flow components. We have these pre-storm stream flow statistics. So that's, what is the flow of the stream when this event starts? Very often that storm flow, that pre-storm flow is not what they call base flow or just groundwater discharge. Very often you have some component of flow from a previous event. Because usually the highway and urban runoff sites start contributing soon after a precipitation event is over, whereas, larger upstream basins could still be discharging stormwater from the previous storm for days or weeks, depending on the size of the basin. So we have that pre-storm flow, and then we use our imperviousness to get runoff coefficient statistics. So we multiply our precipitation times the runoff coefficient statistics for the upstream basin. So we add that pre-storm stream flow and the runoff together, and we get that upstream storm flow. So then we add the upstream storm flow to the highway runoff flow, and we end up with our downstream storm flow statistics. So we get a whole population of events to see what might occur. What are these combinations of precipitation, pre-storm flow, runoff coefficients that might occur over a long period. And from that, we get this population of downstream flows. All right, so in Seldom, we talk about that regional analysis and then the more detailed analysis. So in Seldom, one of the objectives when we were developing Seldom to make it easy to use is that we pre-calculate most of the statistics that you need. So seldom isn't like swim where you have to spend weeks and weeks twisting knobs and dials to try and get a calibrated model. Seldom's calibrated by having good input statistics, and to make it usable, we calculated those statistics for you. So we did a national study. We got, like I said, 20 to 40 years of precipitation data and calculated statistics for 2,610 stations nationwide. If you look over here, you can see that, the cluster of, there's a pretty good density of stations in the New England area. And I guess we have people from Colorado. You can see places like Nevada have relatively few stations. So when you go into Seldom, you have two choices to do an initial level 1 analysis. You can use the EPA rain zone, which it's rain zone 2 for this area. And these rain zones are these kind of black polygons. Or you can use the ecoregion, which are these pastel colored zones you can kind of see underneath the precipitation stations. So in southern New England, we have, I think it's ecoregion 84, which is kind of the Cape and the Islands. Then you have the coastal plains, and then the highlands. In Connecticut and Massachusetts, kind of the northwest corners of the state. All right, similarly, you can select streamflow statistics by region or by using values from one or more of the 2,783 stream gauges that are preloaded into Seldom. So it doesn't make sense to pick streamflow from rain zones, so we use either ecoregions or you can pick some nearby gauges. So let's say my site of interest was in Nevada. You could see these 5 little stream gauges in the middle. If I was out there, I might pick one or all 5 to try and get representative stream flow. So since we developed Seldom, Federal Highway sponsored a study where we did calculations for about 20,000 stream gauges nationwide. It was basically all the data available from 1905 through 2015 now. And if you go to StreamStats, even in Nevada, where they don't yet have StreamStats, anywhere in the country, you can click on your stream gauges and get local statistics. Again, the trick there is kind of knowing a little bit about your basin of concern and knowing a little bit about the station that you might want to pick to try and pick something that's representative. Similarly, for water quality statistics, back in 2004, we did statistics by ecoregion for selected properties. We did data mining from the USGS National Water Information System for 24,581 stations and almost 2 million samples. So even though we did this huge data mining effort, there's not a lot of in-stream data for a lot of constituents that we might be worried about. We're currently doing a project with Connecticut, Massachusetts, and Rhode Island where we kind of went in on a state level basis for the 3 states and some surrounding water quality stations and pull data. So that project will be published later this year, and we'll have you guys will have access to the statistics that we developed at that time. All right, so now to kind of switch gears here, we're going into hydrographs. So when we worked with EPA and the regulatory agencies, we didn't want to cheat. So, right, the old saying is dilution is the solution to pollution. Because the highway or urban runoff ceases soon after the rain stops, we didn't want to use the whole upstream hydrograph to dilute our highway runoff. So this diagram here shows basically the components of the upstream runoff on the left. So we have the upstream runoff, which is the light gray triangle, and that's superimposed on that pre-storm flow. So we looked at a lot of data and we found that the NRCS triangular hydrograph was actually a pretty good approximation for real hydrographs in nature. So the graph on the right, that yellow line, would be the amount of the total storm upstream hydrograph, storm flow hydrograph through time. So it goes from 0 at the beginning all the way up to 100% at the end of that storm event. So what we see down here on the left would be, let's say, a hypothetical highway runoff hydrograph. And like we said, that would cease soon after the precipitation. So that might be short in comparison to the upstream basin, the duration of the hydrograph. So with Seldom, in this purely hypothetical example, this duration 1 might only give us about 15% of the upstream storm flow. So we don't even make it to the peak of the runoff hydrograph upstream. So we don't get to use much dilution in that event. If you put in a BMP and you have hydrograph extension where you're, stretching out that outflow by an appreciable amount of time and say reducing the volume, then we might get out to this duration 2. So if we put in a BMP and we could stretch out that outflow duration, in this completely hypothetical example, we might get up to like 55% of the storm flow. So we get a lot more dilution. So in Seldom, we use some basic basin properties to get the timing of runoff from the highway and the upstream basins so that we can figure out, what's a fair amount of dilution to use. And these values, it's not like the rational method or whatnot that you're only using one values. These values are stochastic. The upstream hydrograph has different lengths based on the precipitation length and basin properties and recession ratios, which are stochastic. And the highway is, again, it's based on basin properties, gives you the basin lag time, and then the duration of the storm event gives you the duration of the highway and urban runoff. And the BMP also is stochastic, so you get different variations for every storm based on real BMP values. All right. Like I said, Seldom was developed as a highway runoff model, but can be used for many types of sites. So here's an example where we're looking at some highway. I guess we have somebody that's not muted. So if you're unmuted, please mute. So in this case, we have 2 bridges over the Charles River in Massachusetts. So when we look at it, we actually have kind of 2 sites contributing runoff. But what do we care about? We care about the sum of the 2 sites that would affect the river downstream of both sites. So in this case, our area would be the area of both bridges, but the timing of runoff would be the flow from like the peak of the bridge to the scupper. So in this case, the flow lengths are shown in blue, the light blue line. And then our slope is our third basin property where we have, so the 2 X's are, we use what's known as the 1085 slope, which has been shown in many studies to be the best slope to use. And so we would use positions, the elevation at 10 and 85% up the flow length. And in this case, it would basically be the camber of the road on the bridge. In Seldom, like I said, our runoff coefficients are based on imperviousness. So in this case, for the bridges, we have 100% imperviousness. And if you want to refine your runoff timing, there's a thing called the basin development factor. We won't get into this, but 0 is a completely natural basin and 12 is a completely engineered drainage system. Because bridges are designed to shed water as quickly as possible, this would be a completely engineered drainage system and we give that a 12. All right, I mentioned scenario analysis. So again, Seldom can be used to model the pre-development condition. So if there's, if I need to put a roadway through here, and the question is, what will be the effect of this roadway? What I can do is I can simulate this natural forested area as the precondition for what will happen when I put a highway in here. So again, our boundary of this little, let's say it's an ephemeral stream, is the yellow area. So the area would be within the yellow polygon. Our main channel is, going down the bottom of this little valley. We might have other like ephemeral channels coming in, but the hydrologic method that we've used, and again, it's been proven in many studies, we only use the main channel length up to the basin divide. And again, these X's are the points at 10 and 85% of the way up the basin. So that's our main channel slope. So before we put a roadway in here, we'd have zero imperviousness, and because it's completely natural, zero basin development factor. So given upstream water quality, which would be to the right of this little basin, we could say, well, what's happening upstream, and if we added in forest runoff, what's going to happen downstream? So that gives us the precondition, and then we simulate what happens, what's the runoff from the roadway, and then we can say, what's going on downstream. I've been mentioning urban runoff, so SELDM can also be used to model storm flows from other land uses. So this is a mall in, I think, like Natick, Massachusetts. So again, the yellow line shows us that we have an area. So that's our boundary to our drainage area for this mall. And again, we use this main channel length. So all these other blue lines are kind of tributary channels from like roof drains and parking lot drains, and they drain into this main channel. And again, the two X's show that we are looking for that 1085 slope to get the timing. So the imperviousness is 99%. So the imperviousness gives you your runoff coefficients. Your area gives you the total amount of rain falling on this area, and the imperviousness gives you your runoff coefficients. And again, a mall has got a completely engineered drainage system. It's designed so that's like would give us our basin development factor of 12. Now, when we look at this mall, we can think of other land uses. For example, if you had a highway maintenance area, you might have parking areas and whatnot. You can lump that area together and figure out maybe what the stormwater contribution is from that area. And again, you need kind of imperviousness, main channel area, and maybe some water quality that's representative of maintenance area runoff. All right. So our case study today, we picked a basin in Connecticut, but for the purpose of talking about how we look at SELDM output, we'll use this Howard Brook, which is a 1.34 square mile basin in Northborough, Massachusetts. So in this area, it's I-290. The basin is 1.34 square miles. I think the highway here is 6.4 acres, and we're looking at the pavement runoff, so the imperviousness of this base of the highway is 1, and I think Howard Brook's got an imperviousness of, I think it's about 5%. So this is what SELDM output would look like. We use Massachusetts water quality data, and what we do is we use SELDM to generate a long period of highway runoff concentration values. And those concentration values are shown as gray here. So total phosphorus concentrations are shown with a log scale on the vertical axis. And then we've got this probability axis. It looks a little weird. The spacing, it kind of stretches out the extreme values. In hydrology, we're worried about those extreme high values, right, for floods and water quality, and the low values for droughts and low flows. So, so these gray dots, what we can do is we can look at the risk of exceeding different proposed levels. If we're looking at a numeric criteria, or we can see, how can we, if we put in a BMP, how can we change the concentrations coming off this site? So we looked at a grassy swale as the BMP for, how would a grassy swale affect the concentrations here? So recently, EPA has recommended a phosphorus limit of 0.02375. Now this is based on, oops, sorry about that. This is based on natural basins and like the 25th percentile of natural basins. So this is a very low phosphorus limit. So the historical in-stream limit is 0.1 milligrams per liter. It's unrealistic to expect that a highway runoff would match, fairly clean upstream basins. If we compared the highway to other discharges, this is a commonly used wastewater discharge limit of 0.5 milligrams per liter total phosphorus. So we can see that about 95% of BMP discharges and highway runoff are going to exceed this ultra low limit. So we can't really apply this background water quality to highway runoff. And we can see that if we try to apply this 0.1 milligram per liter total phosphorus limit, we can see that at that level, the BMP does help because the yellow symbols are below the gray line, but we could still see there's like 50 to 30% exceedance. So we can't reduce those values to meet this 0.1 milligram per liter limit. But we see that the BMP does a better job of reducing highway runoff at the high end. So at that 1 in 3 year limit, which is about 0.5 in southern New England, we can see that even there, the BMP can't quite meet that limit, even though it does a better job. Now, what we can see at the low end might seem counterintuitive. We can see that the yellow, the BMP discharge concentrations are higher than the highway. What happens is if you have like 2 rainstorms in a row, you have a relatively clean highway, when we're thinking our total phosphorus. And if we have a grassy swale, we're taking that pavement runoff and running it over dirt and grass. So we can assume that, at the low end, we're going to pick up some phosphorus. And then we see these weird looking horizontal triangles, the yellow symbols over on the right. Again, we worked with EPA and regulators, and BMPs have what's known as a minimum irreducible concentration. And so a BMP isn't going to produce distilled waters. So what we have is, when highway runoff concentrations are very low, and we can see that our minimum irreducible concentration is set at a basic level. Hang on for a second. Sorry. I think we're all besieged by spam calls nowadays, so I apologize for that. So then we can look at a similar approach at background water quality. So this kind of gets at like, how is the highway an important contributor here? So this is a similar graph where we have total phosphorus and then we have that probability axis. In this case, seldom produces this population of upstream storm flows. So in this case, we have several, the yellow symbols are several different individual water quality data sets, and the blue symbol is the ecoregion value. So we can see that level 1 analysis are ecoregion values like within the cloud of different individual stations. So that's a pretty good starting place with no prior information and without a long-term data set at a site of interest. So we can see if we try and apply this EPA base flow water quality or base flow generated water quality standard to storm flows, even these fairly natural basins, we could see that they're going to, during storm events, they're going to exceed that standard more than 70% of the time. And even if we try and apply the 0.1 milligram per liter criteria to storm flows, we can see that even in the best basin, that's this lower, the upward facing triangles, this lowest value, they're going to exceed in about 10% of events. And that's beyond that 0.5 risk percent risk, which is that 1 in 3 year event. So they're all very much higher during storm events based on that 1 in 3 year event. So then we've generated this highway and BMP portion. We've generated the upstream portion based on the ecoregion data. The question is, how does the highway at this very small basin, Howard Brook, affect water quality? So we can see in this case, we have our blue values are our natural or regional background. There's undeveloped and developed sites in that set. And then we have our downstream concentrations with the grassy swale, our yellow triangles. Our downstream concentration with no BMP are the green triangles, and we can see they all kind of sit on top of each other. So with this site, the DOT could put in a BMP and it wouldn't make any difference because of the upstream basin, even though Howard Brook at like, what was it, 1.34 square miles is a fairly small basin. So based on this regional data, we could say that, the highway may not have an effect. So that would be a risk analysis for an individual event, or not, individual events over a long period of time. We also are worried about total maximum daily loads. For that, we would look at annual loads for that lake analysis. This is the Scituate Reservoir in Rhode Island. The yellow lines are the state roads. So if I was looking at total phosphorus, which isn't going to travel through groundwater, I might only want to look at the areas of these state roads that drain to streams, not the areas such as bridges and whatnot, not the areas that just drain to the local land surface in forested areas. However, if I was doing a TMDL for chloride, well, because chloride travels through groundwater and gets to the stream anyway, in that case, I might want to include the whole area of the state roadway to calculate their TMDL for chloride. All right, that kind of hopefully that gives you an overview of the information we provide. And again, Seldom just doesn't give you one value. It's not like the simple method, and it gives you this population of information. Now, typically for TMDLs, we'd use the long-term average value. So we'd use each of these individual annual values, we'd add them up over the entire simulation period to get that total in the 28 or 30-year load, and then we divide it by the number of years to get that average load. And what Seldom gives you, you can calculate those average loads, but it also gives you the variability in loads from year to year. So with TMDLs, you have that margin of safety. So that uncertainty and variability can inform, how you do the TMDLs. And also Seldom gives you information about how a BMP may help. So we see in this case, even though the grassy swale may not be considered a great BMP, they're pretty much everywhere, but we can see that we get substantial reductions in the highway runoff by using just a simple grassy swale. And you might ask me, you might say, oh, when we looked at the concentration graph, it didn't look like the grassy swale did such a great job, but grassy swales infiltrate runoff, so that reduces the load. But also, if you remember that the grassy swale was able to shave off those very high concentrations. So it didn't do a great job at the low end, and at the very low end, even grassy swales might have higher phosphorus than the highway. But in those large concentration events where it really matters, it can really shave off the concentrations. And if it's shaving off the flow, then it's reducing the total loads. All right, so hopefully that gives you an overview. I haven't completely bewildered you at this point, but to help, what we'll do is we'll go through Seldom, and you can get a feel for, how to use it. Seldom has a graphical user interface. It's got a series of forms. So the first three forms are the analyst, that would be you. The project, again, that can either be an actual highway project someplace, or it could just be a collection of related analyses. So the analysis is like that folder in that file cabinet drawer. It holds all the related information to get an answer or a set of answers. Then we look at the site and region forms. You click through you put in your highway hydraulic information. It tells you the grid form, just lets you know that you specified your latitude and longitude correctly. Your ecoregion, you can either use the default ecoregion based on your location, or if you know you're kind of up against the boundary and you want to use a neighboring ecoregion, you could do that. You can specify your upstream basin characteristics. If you're doing a lake analysis, you can put in your lake basin information. If you're not, you won't see this form. Then you get into hydrology, you do the precipitation, your stream flow, RV is your runoff coefficients. Then you get into water quality, you have your highway, your upstream and your downstream water quality. And then you put in your BMP characteristics and then run the analysis. All right, we've kind of gone through that. If you guys want to open up your microphones, if anyone has any question at this point, I'd be happy to answer any questions before we kind of dive into the case study. All right, I always say that lack of questions is either really good or perhaps, let's see, somebody has raised their hand.
Hi, it's Tracy Iott from Connecticut.
Hi.
Can you either now or when appropriate talk about whether there's any ability to use output from other models such as HSPF to parameterize the Seldom model?
If you use HSPF, you can, if you're looking at generating stream flow record at a point, you could use HSPF, calibrate that to the long-term record, and and come up with a stream flow there. You could probably also, well, HSPF, the models I've seen by very talented modelers, they just kind of use regional precipitation statistics anyway. So they may grid precipitation, but they may not really be getting a good answer. If you're interested in kind of gridding precipitation on the Seldom website, Adam Stonewall in Oregon did a pretty good job of coming up with like a state map where he kind of calculated. So HSPF will match, like you can turn those knobs and dials and to get a calibrated stream flow at a point. So it's good at that, but my understanding of the water quality modules aren't so advanced. It's kind of a case where you have a very complex model with a lot of knobs and buttons, but without sufficient data to calibrate it, you can get answers that may not be as good as having a complex model might suggest. Does that make sense?
Yeah, no, it makes sense relative to the complexity of the model. I was thinking more of if we don't have the water quality data necessary to parameterize Seldom, then maybe HSPF could fill in that gap.
For Southern New England, we have, and when the report comes out, we've collected data from like 80 sites and come up with the statistics you need for it.
Okay. Great.
So yeah, again, models are only, what comes out of a model, including Seldom, is only as good as what you put in. So if there's not great water quality data around, HSPF might give you a false impression of what you know. Like if you don't have much data and then you use a model to make up data, sometimes that may or may not give you, be really giving you the information you need.
Okay, thank you.
It would, however, I guess if you have like wastewater treatment plants in there, it might give you information of, what your flows might be for wastewater treatment. Also, I think, are you running HSPF on a 15-minute basis or a daily basis?
15-minute or maybe smaller.
All right, so that might give you some information that you can't otherwise get.
Okay, thank you.
And I think HSPF uses water quality transport curves, which we do as well, to get like kind of random random water quality data and kind of relates that to flow. All right, are there any other questions? All right, so I guess I'll roll into the example. I'll just go over a quick presentation for a Connecticut watershed to kind of give you an orientation, and then we can all fire up Seldom and use it to run through. So let's see, did I do the right one? All right, yes. So right now we'll play with Seldom. We'll run through the interface. We'll play with the controls. We'll look at the question mark, help buttons. We'll enter some numbers, run the model, and take a first look at the output. The interfaces of Seldom aren't designed for presentation mode. They're kind of the size. They're sized to use Seldom kind of on a desktop with some other windows open. So I went and Googled how to zoom in on a team meeting, and I practiced it. So if you hold down Control and like rotate your mouse wheel up, it will zoom in. Or if you do, it looks like Control plus equals. So I guess the plus isn't holding down the plus. I guess it's just Control equals. And to zoom out, you get that Control and negative, or Control and rotate the mouse wheel down, and Control 0 should get you back to normal. And again, Seldom has this GUI. We'll step through each form and kind of talk about what we're doing on each form. So as I mentioned, Seldom is a lump parameter model. We use the same variables for the highway site and the upstream basin. We just use different values. So the big one is drainage area. So the drainage area isn't the actual land surface. It's, if it's like if you're looking down on a map, what's the map area? So that's the drainage area. Our main channel length our basin length, our main channel length, is the length along the channel all the way up to the extended up to the basin divide. So it's not the straight line crow flies length. It's following the undulations of the river or the meanders of the river as it goes up. Again, for the highway, we usually look at the pavement to see what the pavement is contributing, and that would either be the length, from the basin divide through the stormwater system or down the edge of the road, or, if there's a swale, basically the length from the divide to the outfall. And for a bridge, as we mentioned, it would be like the crown of the road to the scupper would be the length for a bridge. So those are usually very short. Research has shown that the best slope is the 1085 slope. So that's 10% up from the outlet to 85% up from the outlet. So you just find those two locations on the stream, and then you look at, you can look on a topographic map and subtract the two elevations and divide by that length between those 2 points. So the 1085 slope is best is because, the runoff from the peak of the hill might get to the 85% point very quick, but that doesn't control the overall time. And the last point might be a little bit steep, on stream basins might be not have as steep a slope, but when that water arrives at that 10% point, usually it's a short distance. Even if the slope is low, the water still gets there. And again, it's the same principle for the highway site that we're looking at these basic basin properties. The other that The other variable is the total impervious area, which we're probably all familiar with if you're on this. It's the areas of roads, roofs, and parking lots for the upstream, and usually the area of the pavement for the highway. The impervious area controls, you multiply the rain times the runoff coefficient. So your runoff coefficient statistics are based on the area, and your the timing of the hydrograph, which we saw was also important, is also based on the impervious area. So the case study will look at Chapin's Meadow Brook. Hopefully I'm saying that right. It's actually, I think it's a 0.76 square mile basin in Tallinn, Connecticut. So we're looking at this small basin above I-84 in Tallinn, Connecticut. So I'll put these in the chat. So what we want is the latitude and longitude, and the latitude and longitude in Seldom will give you your, it will tell you what ecoregion you're in, so you can pick water quality, precipitation, and stream flow by ecoregion. And in terms of documentation, so to get your regional values, your latitude and longitude can be pretty rough, like the size of a topo map. So, about 1/4 of a degree. For documentation purposes, if you're saying I'm looking at this particular bridge, you might want a location that's more precise like this one, or if you want to give people enough information that they could go to StreamStats and get their own basin properties, you might look at providing a more detailed latitude and longitude. So the area contributing to this brook is 7 acres of pavement. And as I mentioned, Chapin's Brook is 0.76 square miles. The channel length that we measured from using Google Earth is 2,716 feet for the highway and about 8,000 feet for the brook. And our slope is 223 feet per mile for the highway and about 263 feet per mile for the slope. And again, we're modeling the pavement, so our impervious fraction is 1 or 100% TIA for the highway, and only 5.44%. We'd enter a 0.0544. And I've mentioned the Basin Development Factor, or BDF. If you put a value of -1 into Seldom, it will tell them that you're not messing around with this variable. You're just using the imperviousness for the timing of the hydrograph. So again, once you put in your latitude and longitude, you get your precipitation statistics, you get your stream flow statistics, you get your water quality statistics. All right, and here's some example results, but now we'll kind of dive in and try and use Seldom together, or I'll demonstrate it for you if you don't have it ready. So let's see. First, I guess I'll put the basin properties in the chat in case you, let's see. In case you don't have 2 screens. Let's see. Yep, looks like you can grab that and upstream. And all right, now let's fire up. Seldom. So once you fire it up, you should see the entry form here. You might have to enable content. So I'm going to kind of shrink the window a little bit. So if you need to zoom in, you can still see it. All right, and again, it would be control and roll your mouse wheel up will help you zoom in, and control mouse wheel down will help you zoom out when the time comes. All right. So when you come here, it will give you version information on the first page. Seldom will have explanation buttons on every form. We have the proceed button to do a manual analysis. Thanks to Federal Highway, and the impetus was from North Carolina DOT, we added a batch run in Seldom version 1.1. And you can exit Seldom. So every form has exit Seldom, so that, you know, if it's time to go, you have to pick up the kids at the bus stop, you can click exit Seldom and get the heck out. So now we'll proceed. So the first section is the analyst. And we can see on most of these forms, once you get used to them, they all have the same look and feel. I try to use the same or similar approach to each form. So what you have up in the upper right is information. So the information form will give you, you click on that and it will tell you, you know, what's going on in this form. The text is there, it's public domain. So if you're using Seldom and you need to write up like a report of your results, you can come here and you can copy these. You can copy the text and kind of paste it into whatever report you have. So yeah, I just pasted, you know, the text in there, and then so, you know, you can paste it into Word or whatever. So when you come into one of these Seldom forms, usually you have what's called a combo box up here. So you can choose one of the existing. So we have anonymous is typically what we use. For the Southern New England project, we added, you know, U.S. Geological Survey. So on the forms, you can choose something. You can either select what you already have, you can edit the current thing, or enter a new thing. So let's see. So if we pick anonymous, we have anonymous. You can see if we edit this. So the analyst form, if you do an environmental impact statement, EPA wants to know about the people who did the analyses. So you can, if you look up here on the right, you can see required fields are usually bold and an asterisk. So so for almost every choice, the initials / short name is required, and that's only because once you define it, it'll be available up in the pick menu or the combo box up above. But you can put in your last name, first name, middle initial, salutation, organization. For an EIS, there's these roles, either your primary, secondary reviewer, or an examiner. You can put in your address and contact information if you want, and notes, but none of this is required. So to kind of get in the spirit of using Seldom, let's enter a new analyst. So if I enter a new one, you can see everything went blank. So now if I just, my short name would be Granato, let's say, and Gregory Granato. So at this point, the only thing that's required for this, again, is the role, which is automatically selected, and then the name. I didn't even have to put in my last name and first name. So I accept updates. And you can see that locks, accepting the updates locks the fields. And then now I'm added as one of the choices on the form. So I can pick me, or I can go back to kind of anonymous mode. If I pick me and then I edit, then I could add my middle initial E and US Geological Survey. So if I accept the updates, again, it locks the form, and now I can proceed. When you're in edit mode, you can't proceed because you're editing. You can go back and you can exit. So if I have to leave for an appointment, I could click exit now and get out. But I'm just going to select this current and I'm going to proceed. Now, a thing to note is that Seldom makes a whole series of export files. Everything that you put in here will be echoed out. If you don't put it in, it won't be echoed out. So the question is, are you doing, just kind of a draft analysis just to get the feel of something, or are you doing an analysis, say for a regulatory purpose or a documentary purpose where you really want to record everything? So there's a number of places where you can put in more or less information. So we can see that there's a whole bunch of different analyses available. Some of them are pre-populated, the non-interpretive ones from the upcoming report, like the highway runoff and urban runoff yields, and some of the structural BMP importance. But and Z01 is the example project. That's the original one that came from Seldom down in Pennsylvania on one of the federal highway sites. So let's stick with 16, which is DOT simulations. So again, we have information. It tells you what a project is, what I'm doing on this form. And again, we have select, edit, enter. So we have we can see if we edit, we mentioned that, our primary organization for these analysis are Connecticut, Massachusetts, and our Rhode Island DOT. This is our project ID number, Federal Highway Administration, and it's just got a short summary. Simulations for New England DOTs to use for stormwater runoff scenarios of potential interest. Here's our system variables, which are preset. They're required, but they're preset. And then our project abstract. I can put as much or as little information as I want in this. But for this, we just say this project contains analyses for DOTs to evaluate stormwater runoff scenarios. So at this time, I don't really want to change anything here. So you can see I have accept updates, but not proceed. I will click select current project to go back so that I can proceed. So as I mentioned, that the project is like a drawer in a filing cabinet. If I set up sites and information for this project, I don't necessarily want all those choices available when I go to do a different project because, the upstream basin and the site may not be relevant to that project. So that's kind of what a project will give you. It kind of segregates out information that should be separate, and then there's some information like water quality concentrations that you want available to all projects. So that kind of information is available everywhere. All right, let's proceed. I've picked my project. And now we can see we've come to the analysis. And I don't have any choices. So this project, I haven't done any analyses, so there's no choices. So this is grayed out. And I can't select a current, I can't edit a current, I can't copy a current. I can only enter new. So here's one of our question mark boxes. So this is basically, I found developing a lot of software that no one ever reads the manuals. So I tried to put the manual in the interface. So where you see these question mark boxes and you click on them, it will tell you about, how do I use this form? What's going on here? All right, so let me bring up. So we're going to look at Chapin's Meadowbrook. And this will be, so we'll do ecoregion water quality. And so USGS does QW for water quality for some weird reason. So our analysis options, so this is just draft, final, or supplemental. It's just for environmental impact statements. Again, it will tell you about that there. We'll just leave this draft because it's, we're just kind of messing around today. Master random seed. So computers can't really create random numbers. So they use what's called a pseudo random number generator. And these number generators have to start someplace. So that's what the seed is for. And again, if you want some more gory details, you could see that the explanation for this is pretty complete. And so because we don't have an analysis, we have to generate a new one. And we can do a stream basin, a stream and a lake basin, or just a lake basin. So right now we don't want to mess around with lakes, so we'll just pick a stream basin output. Now analysis description, so we can do 2022 class example using ecoregion water quality. And then I'll accept updates. I've specified everything. And you can see now that I have something, I can pick it. Well, until I have two things, picking it doesn't make much sense, but now I can edit it. And we can copy it. So we won't copy it now. We'll copy it later. So if I go to information now, once I get to analysis, I can see the analysis status. So this is just a little interface, and as we go through and specify things, these little checkboxes will get checked. So if I come back here tomorrow and I don't remember where I got on this analysis, I can open, once I get to the analysis, I can open this little sub form from the information form and see where I left off yesterday. If I'm going to copy an analysis, usually you want to go all the way through and specify a whole analysis before you copy it. So that's where this is useful. And again, this just tells you about what the analysis information is. Okay, now we've created an analysis. So we've created a folder in this project file drawer. Now let's proceed. So the first thing we have is the highway site. So if you go to your chat, first thing we want is our name. So we'll call it I-84 at and you can see that we have 50 characters here. Usually that's to fit in the choice. We have our pavement runoff both ways. I've put the latitude and longitude in the chat. And I'm just going to paste them in. You can paste them in or type them in. So then again, we have the hydraulics. These are the hydrologic variables we need to know how much precipitation we're going to get from this site and what's the timing of that. So for the highway site, we have the 7 acres. We have that 2,716 feet is the length from the basin divide to the stream. And we have 223 feet per mile, an impervious fraction of 1. And again, we're going to use the impervious fraction to figure out what the timing of the hydrograph is. I should say also, when I hover over something, when I click into something, you can see down on the status bar, it gives you information. And when you hover over it, it gives you this tooltip text. So in theory, that would help, you know, with the 508 compliance. So I think that helps people with like who are visually impaired, and it, you know, it will talk, their computer may talk to them and tell them what's going on based on these hover text. Also, again, we have all these question marks. So if you get here 3 weeks from now and you say, well, what the heck is the drainage length? You can click on this. Well, this isn't a long definition, but it tells you what's the drainage length. I think the BDF might be more complex. Yeah, this will, if you want to know what the basin development factor is, this gives you the whole definition. All right. So the hydraulics, you can see they're bold, they're starred. Those are the required fields. The short name, the latitude and longitude, bold, starred, you have to put that in. The other information, again, this is just documentary information. If you put it in, it will come out in the output. If you don't, it won't. So you can put in total lanes, lane widths, average daily traffic if you want, pavement material, type of curbing. Curbing has been shown to have a effect on water quality because it kind of traps stuff on the roadway for runoff, whereas country drainage stuff tends to blow off into the, you know, median and shoulders and not be so mobilized by runoff. And here's the site description. I can put in as much or as little information about this highway as possible. So I have my name and location. Right now, we're not going to put anything in here, but you know, if this was a real case, you can put as much or as little. You can put in citations, or you know, if there's a certain highway map that has a certain ID number, you could put that in. But right now, I'm going to accept updates. And this just is a little nanny state message, just to let you know you picked -1, so the basin lag equation using the basin lag factor imperviousness will be used. So if I click OK, so now I have this highway site. And let's say I know that this is the condition that exists, but I want to look at like if I added more area. So what I can do is I can copy this. So if I click copy, I guess you guys, I should read this since we're in class. You have selected to copy the current site option. This option will create a new highway site using information from the selected site. The user should complete the input process for the selected highway before making a copy to modify. Changes that are made as the copy action will not be saved until the copy button is clicked. The cancel copy button will undo any changes that are made and revert to the previous selection. Once copy button is clicked, however, the user cannot cancel or undo the copy action. And then, yes, I want to do that. So I-84 at Chapmo, so it comes up automatically with the word copy because you have to have a different selection name. So we'll just call this one 8 acres. So I'll add this. And so I'm just going to widen the lanes or add lanes. So this one is going to be 8 acres, where the length and the slope and the imperviousness will stay the same. Now, if I started this and I don't really want to, do this, I can cancel the copy, but yes, I want to do this, so I'll copy. And it reminds me my basin development factor of -1 means I'm using imperviousness, so I'll say okay. So now I've got Chapin's Meadowbrook at 8 acres, or I-84 at 8 acres, and then I've got this one at 7 acres. So maybe I want to go back and add 7 acres to be more explicit. Maybe existing. And so I made a change. That change won't occur unless I click accept updates. And again, it gives, some of these messages can get annoying after a while, so I apologize for that. And let's proceed. So now we've specified our highway site, we've given it a location, we've filled out the hydraulics, and we're ready to go. So this GIS form is just it just lets you know that what you selected is in the grids that we use, so therefore our rain zones, our ecoregions, etc., are available to you. You could use Seldom in Great Britain, but you know, all the background statistics, or I guess up in Canada, but all our background statistics aren't available to you. Sometimes if you're near the coast or perhaps near Canada and you're not using a precise latitude and longitude, perhaps you might be over the edge of the grid, in which case, you know, this would give you like a red warning message and you'd go back and fix it. What I tend to do sometimes is I forget the negative number on the longitude. So, you know, that lands me in Kazakhstan. So we don't have any data for Kazakhstan, so it tells me I'm off the grid. So I say, oh yeah, I need the negative number for the longitude, and therefore I go back, put it in, and everything looks great. All right, we come to the ecoregion form. So based on our latitude and longitude, it says we're in this northeastern coastal zone. Now these are not in order of proximity on this form, they're just in order of ecoregion number. So if you know what ecoregion you're in, the other thing you can do is all these drop-down menus have autocomplete. So if I say, well, I'm more on Cape Cod than in northeastern coastal zone, so I think that's 84. So if I start typing 84, yeah, that's the Atlantic Coastal Pine Barrens. So that's Cape Cod. I think we have people here from New Jersey. I think you guys have a lot of Atlantic Coastal Pine Barrens too, Long Island. So I can pick this one. So I typed it in, it showed up, but I still have to click on it. So yes, that should have changed what's on. Oh, it went back to. Okay. And that should be updating. I guess it doesn't like that. No. So it's making a liar of me today. Interesting. Let me go back, proceed. Okay. So somehow I messed up the form, but if I hadn't done that, so I guess maybe on the ecoregion form you don't get autocomplete. It looks like you do, but you don't. So the other, well, I guess that's a, if you want to reset a form, you can go back and then proceed. So we can see we have neighboring ecoregion. So on this tab, the green, basically, the Seldom cells are about the size of a USGS quad sheet. So if you're on the boundary of an ecoregion and you come to this form, you can click on one of these, you can move around. In this case, you can see I'm in ecoregion 59 and I'm surrounded by 59, so it's pretty clear that I'm not there. Now let's go back and choose 84 and it should allow me to. Oh, no, I guess maybe at some point I disabled changing your ecoregion. All right, I'll have to look into that and make sure I didn't change something in the background with the latest version. So now we're at the upstream basin site. So it's the same as the highway site or a similar form. So we just need to put in information here. So in this case, that was I-84 at Chapin's Meadow Brook. In this case, because it's the upstream basin, we'll type in Chapin's Meadow Brook at I-84. If there's another state roadway, numbered state roadway downstream, this helps us, the latitude and longitude tells us where we are, but also the description. And in this case, I'm just going to copy this into the full name, but you can see we don't really need a full name. And our basin description could just be kind of a short, I think it's like 250 character narrative description. So what we really want is the hydraulics. So the highway is in acres, but the upstream basin is in square miles. So I'm just going to copy this stuff over from the chat. Let's see if I copy over the comma. I think it's okay with that. And let's see, easier to type. And 0.0544 was what StreamStats told me the imperviousness was. That's probably a little too precise. But so again, it's the impervious fraction is between 0 and 1. So 100% imperviousness is going to be an imperviousness of 1. And again, my basin development factor, I'm going to use imperviousness instead of putting in a value between 0 and 1. So I'm going to put in a -1. Now, hydrograph recession is the ratio of the rising limb to the falling limb of the hydrograph. And again, in this case, what we've done is we've published a report where we looked at stream basins nationwide. And in the latest report that we're doing for Southern New England, we did some more hydrographs in Southern New England, and we have values there. But our analyses show that these national values are actually pretty good. The hydrograph recession, because it's not, as familiar to people as the imperviousness, we have some explanation on the form. Again, we have, a detailed description of what this is, if you're wondering what it is. And while we're in the information form, we'll see the analysis status. So you can see right now we've done this highway site and the ecoregion. So I'll close this, And so I've specified everything I need to. I'm going to accept updates on the upstream basin. And again, I get that message. And you see now I've defined something. I have that as a choice. Again, I could copy this upstream basin. Let's say I wanted to look at if this was a hypothetical highway at this point, like we're going to build a new highway across Connecticut, and I'm worried about this brook because there's some endangered species there. I might want to say, well, if I went with alignment A, the upstream basin might be, 0.76, but if I go with alignment B, it might be 3 square miles. It would be, the decision would be based on a lot of other things besides water quality, but I could, by looking at the 2 locations on this brook, I could see, if I move the highway downstream a little bit, does it make a difference to these, endangered species? So now we can see that all the buttons are gray. Again, I can exit seldom. I can go back to the previous form, or I can proceed. All right, so we talked about the precipitation statistics. So in the Southern New England application, we've pre-populated a choice of Southern New England, 45 stations. And even though I didn't pick the ecoregion based on ecoregion 84, since we pre-populated those statistics for this project, they're available to me, even though my site isn't right here in the Atlantic Coastal Pine Barrens. So I have these different values. And again, you can see select current, edit current, enter new. So again, the form is blanked out because we've specified them. We won't get into the individual precipitation statistics, but if I edit this, let's see, because it's, so if I say edit on this, then I have to generate or examine the statistics. So for this, this comes to this form where I can pick the stations that I'm using. So I'll close this. I won't mess around with this one at this time. And we can enter a new definition. So once I do that, I give it a name here. I can do rain zone average, rain zone median, ecoregion average, ecoregion median, selected station average, selected station median, or I can type in my own. If I have my own rain gauge and I want to use those statistics, or if if I'm Adam in Oregon and I've created a contour map for the state and I'm at a certain site, I could use those precipitation statistics from my contour map. All right, at this point, I don't want to do a deep dive into the individual statistics. We just kind of want to click through the interface. This is like the trust Greg mode of clicking through the interface. So we use the EPA definition of a precipitation event, and so that's what we'll do. So since we're doing a level 1 analysis, let's go with this northeastern coastal zone precipitation. And you can view region information here. If you want to, again, if you're doing a report on an analysis, you can copy that information. And this gives you all the sites, the precipitation sites in this ecoregion. So this looks a little bit ugly because it's tab delimited text. But if I go and I open a spreadsheet, so if I hit Control C for copy, and then I come to a spreadsheet and I can paste that in. So it gives you the station name, station number, name, latitude, longitude, and these are all the NOAA stations with at least 24 years of data. And we can see for this ecoregion, we have sites in New Hampshire, Massachusetts, Connecticut, and Rhode Island. All right, now I can close this form and now I can proceed beyond precipitation. And now we go to streamflow statistics. So we want to select our statistics. And again, like I mentioned, that right now, pre-selected, we have our median of Southern New England index stations. So for the people at DEEP, we selected index stations and used those to supply information to the safe yield tool that we built for you guys. We decided, because those are good index stations, we decided to add them to sell them. But let's enter a new definition since we're doing a level 1 analysis. And again, I want to use my ecoregion median streamflow statistics. So it gives me information, select streamflow data set, click the statistics, and then click the accept button. So we can see we have the federal highway, we have the Southern New England data set, and the Southern New England index. What you will see outside of this project is the Federal Highway Administration. So I pick that data set for streamflow statistics, I pick ecoregion median, and I generate examine statistics. Now, again, I can view related sites. Oops. I have to accept the updates. Now I can view related sites, and again, it might look ugly in the text window, but once I go to Excel, if I'm building a table or I want to check the statistics, I just copy that, Control C in that window, and I paste. And so there's 79 streamflow gauging stations in the federal highway data set for this ecoregion. All right, so now I've selected my streamflow just by picking the ecoregion median, and now I can proceed. Okay, the runoff coefficient form is almost just an information form, but you can make some changes. So again, we have information here about the different equations. So this is the highway site. So by using the highway equation and giving it an impervious area, we get an average runoff coefficient, a standard deviation of runoff coefficients, and a skew of runoff coefficients. So the Monte Carlo model generates a bunch of different runoff coefficients. It's not like the simple method. It's not like some watershed models where you get the same runoff coefficient every time. Based on actual data where people are measuring it at the sites, runoff coefficients change from storm to storm. For example, if you think of the curve number, they worry about the antecedent wetness. We don't have to specify that. We just know that they vary randomly. So if I do the seldom highway sites, so the highway site's 100% imperviousness, so that's a fraction of 1. I get these values for the average standard deviation and skew. So I want to use the highway sites. We use the upstream basin equations, and again, I can look at this and I click the question mark button and it will give me those equations and information about those equations. And all this stuff is documented in a series of 3 federal highway reports, a number of USGS reports, and the USGS techniques and methods manual for seldom. So all this stuff, if you want to dig deep, all the information is published, peer-reviewed, and available to you. So in the upstream basin, we got 0.054, so we can see our average runoff coefficient's about 0.14, and there's our standard deviation and skew. In our research, we found that the best predictor for your runoff coefficients in a stream basin was the pre-storm flow. If it's higher, that makes sense because the basin is wetter. So if you have the same amount of rainfall, you'll get more runoff from a wet basin. So that's how seldom does that stochastically. It's not locked 1-to-1. A wetter basin doesn't necessarily mean that you have higher runoff coefficient. It just says that they tend to be higher. So the Monte Carlo model uses that correlation to build that into the generated values. So we can see this one's pretty easy to use. For your upstream basin, you can use the seldom highway equation. You get slightly less, you get a lower average, different statistics. You can use the Schuler's trim NERP equation. So that's National Urban Runoff Program. I put that in there because it's used a lot. Without getting into too many details, Schuler vastly overpredicts the runoff coefficients at the high end, which can be very important for decision making. If your actual runoff loads aren't as large as your simple method runoff loads, you might be spending a lot of money on a TMDL when in fact there may not be a problem. And you can put in user defined. So if somebody asks if you have a calibrated HSPF model and it says that the runoff coefficients for urban areas are this, without getting too far afield, HSPF is a distributed watershed model, but if you really look at the guts of it, it has what's called HRUs, so it's hydrologic response units, so it's really a lump parameter model kind of that seems to be a distributed model. So for your urban HRU or for your pavement HRU, you can use those runoff coefficients if they're calibrated for per area. If you use this user-defined option, you can see now these windows are blank, so you can put in your own values. So the seldom equations, highway and non-highway, are based on data from, I think, 77 highway sites, and I think we had data from 306 non-highway sites, and I think and sufficient data to do statistics from about I think 136 sites. So once I'm here again to proceed, I need to accept updates. Pretty much 99% of the time, you can just kind of click through this form. You can use the information and statistics we provide for you. So if, before I proceed, I'm going to click this information and analysis status. So you can see now that we've clicked through that, you can see we're making progress. We're almost there. So I can close this information form. Oh yeah, here you go. There's a whole bunch of text on the statistics for the runoff coefficient. So I'm going to accept these updates, or actually I'm just going to, let's see, yes. If I think I may have made a change and I'm not sure, again, I can go back and then proceed, and it will come back to the original condition. I accept updates to proceed. Now we get to the water quality form. Water quality is a little more complex. So we start out with this general explanation. You can see in this text, we have instructions for this form, and we have information about the ecoregion that you picked, because we can pick water quality by ecoregion. So we'll have a presentation on this on a different day, but seldom can create highway runoff statistics randomly by using the average, standard deviation, and skew of real data. So we have pre-populated a whole bunch of concentrations for highway and urban runoff. Highway dependent is a dependent relation is when you simulate one chemical or constituent and then you simulate another one from that. So for example, organic chemicals and metals tend to travel with the sediment, and they're more expensive to collect the data for than for sediment. So you can often use sediment to predict concentration of those other constituents. So you might want to use sediment, which is cheap to collect, so you can get a lot of data to predict other things where you may not have as much data, but they may be associated. So for example, there's a lot of TSS, total suspended solids, data from highway runoff studies because it's kind of the regulatory sediment compound. But research shows that the TSS, total suspended solids, is a really not a great measurement. And I can go into that if somebody wants to talk about it over coffee sometime. But USGS has determined that it's fundamentally unreliable for receiving waters. So we measure a lot of suspended sediment concentrations, but very little TSS. So this equation lets you predict suspended sediment concentration, or SSC, from your TSS because TSS is widely available. Similarly, upstream random, it just uses the average, standard deviation, and skew of the upstream water quality. And in our research across the country, we found that pH is fairly random. It doesn't vary that much, and it doesn't vary with flow. It just randomly varies. Now we have upstream transport curves. So a transport curve is a relation between stream flow and water quality. So if you have like something associated with a point source, like a wastewater discharge or groundwater discharge, when you have more and more rainfall runoff, those things tend to get diluted. If you have runoff associated things like sediment and, phosphorus from runoff, those tend to kind of go up with flow. So, and sometimes you can have different behaviors over different ranges. So the transport curve, which can have low end, medium, high end, can simulate how water quality varies with stream flow. And again, upstream dependent, that's where you have data that you can get and you might predict something else. So if you look down here, you can see we have PAHs, or polyaromatic hydrocarbons, from soils near pavement. So there's very little data for total PAHs because each PAH sample you send to the lab costs at least about $1,000. So, even for highway runoff, there's not a lot of PAHs versus, if you look at suspended sediment or phosphorus. So, all right, we've kind of gone through this form. Well, then we have our downstream pairs. What do we worry about? We worry about, we pair the highway runoff and the upstream water quality, and we want to know what's happening downstream. So let's go back and select some highway runoff. We'll select a transport curve, the ecoregion transport curve, and then we'll create a couple downstream water quality constituents. All right, before we do that, let me take a little break. All right, so in the water quality forms, I tried to, follow a standard protocol. So once you get familiar with them, you'd get familiar with them. So things that are available tend to be in the lower window, and then once you pick them, they go to this upper window. On the top window, we have two choices. We can view things. So if you click on something up here, it will show you, or you can deselect it. So once you pick something and you change your mind, you can deselect it. Down below, you can view something, you can edit something, you can delete something, and then you can define a new one. So in a later run through, we'll talk more in detail. Right now, we're just going to pick a few things and get to running Seldom. So you can see I've got these descriptions, short description. We have HWI for highway, fecal strep, and we've got this P code is USGS. And for the highway, we had our median concentration estimate. We did a low concentration estimate and a high concentration. So let's just kind of scroll down and we'll do total phosphorus. And let's pick the median concentration estimate for highway runoff. Now I can pick a whole bunch of these. I could pick all of them and run them all in one scenario. And in fact, when we did the total maximum daily loads for California, we ran them all in the same scenarios. Because it's a Monte Carlo model and it uses this seed, it creates different populations. So if I wanted to create the same population for the median and the low, the same rolls of the dice, then I would run each analysis, or I'd run two analyses, one with one and one with the other, so that they'd be 100% directly comparable. I could run them together, but they'll be based on different random combinations. That might be a little too much information for day one, first run through Seldom. All right, let's go to the upstream transport curve. So that's my highway choice. Let's go to the upstream transport curve. And you can see we've pre-populated a whole bunch of information for Southern New England. We did the same thing for Oregon. In this case, we're looking at in the project in Southern New England, we're looking at the question of what's the difference for the different individual station. So you can see in the Southern New England application, we're going to have individual phosphorus values for individual stations. And let's see, I think if I come down, so you can see there's a lot of choices. So if I just click ecoregion equations, you can see I have my ecoregion SSC, suspended sediment concentrations, my ecoregion total hardness for ecoregion 59, and my ecoregion total phosphorus for ecoregion 59. So right now we're worried about total phosphorus. So I'm going to pick that. Again, it tells me what I've picked. It gives me some information. If I wanted to edit this one, again, if I want to view it, I click it, and then this comes up. And again, I can copy this into my spreadsheet. So if I start a new tab, there's my water quality information, so I can put that into a table. Let's see, and if I wanted to edit this, if I click on this, I come up with this form that's designed to enter or edit water quality constituents. And this says, yes, it is an ecoregion value. So right now I'm just going to close this because I really don't want to, and we'll get into, entering or modifying a water quality definition in a subsequent run with Seldom. All right, I chose total phosphorus. I should have predefined the pairs for you, but I did not. So let's do that now. So let's define a new pair. So we want to look at this combination of median highway runoff and ecoregion phosphorus. So we hit this define new. We say yes. So we'll call it total phosphorus ecoregion. And then median highway runoff. Again, we have 50 characters, so I'm doing a little shortening there. So I give it a name. Everything has to have a name. And what parameter do I want? So I want total phosphorus. So again, we've got like 7,000 parameters. These are listed in order that they're measured, I believe. In this case, let me click off that. And if I click in here, and I can start typing phosphorus. Oh. There we go. If I put in P for phosphorus, it comes up. Even though it's here, I have to click on it. So I click it. And now you can see it's limited my selection to what we've defined, or I could still go in and pick one of the other phosphoruses here. And if I pick those, it would add them to the other list, because you have to simulate both phosphoruses to get the downstream value. And again, we have our ecoregion 59 phosphorus, and then we have all these different individuals station phosphorus values. We also have our minimum, our median of minimum developed site, our median of developed sites, which we are less than 5% impervious, greater than 5% impervious, and then we have our wastewater affected sites. So if we wanted to look at phosphorus using those, we could. But right now, for this analysis, we'll use these ecoregion values. So we want to know what's going to happen downstream with and without a BMP. So this one, I'm not going to check BMP, so I'm going to call this one no BMP. And then I'm going to accept these updates. So now I have this choice, no total phosphorus, ecoregion, median, highway, runoff, no BMP. So let's enter a new one. Let's do it with BMP because I want them both. So let me see. So since I'm lazy, I like to copy things. Whoops. Let's see, select current. If I edit current, yeah, I could have typed it by now, right? When I do these downstream, I'd like to name them exactly the same, except no BMP with BMP, because it helps pick them. So I'll use W for with BMP. So again, I have to pick phosphorus. So if I kind of highlight this field, whoops, and start typing P, phosphorus comes up, but then I still have to click it. I have my highway phosphorus came up because I've already picked that. My total phosphorus came up because I picked that. And then we have use BMP, and then I accept updates. So now I have those two, and I proceed. And then I just want to come down here, find them on the list. Let's see. So you can see we've defined a lot. It's here we are, TP ecoregion median highway and TP with BMP. So now I've selected these. So now I proceed. So the default is no BMP in place. So even though I said yes to BMP to one of the definitions, unless I specify a BMP, it won't apply it. So we'll just take, so we just did a report where we used all the data in the International BMP database to calculate statistics for different BMP categories. So right now we're just going to use the median performance BMP. And this gives you information about the documentation, the hydraulic statistics, the water quality parameters for that BMP, and then the water quality treatment definition. You can look at the definition for individual constituents. So I don't really want to do anything to this definition, so I'm just going to proceed from here. Then we come to the seldom output form, and we just have to click run seldom. Well, we have choices. We have our plotting positions, could be percentiles, which is typically what graphing packages like. So that's our default. Descending order means that your low probability events will be the highest concentrations, flows, and loads. And that's usually what you want. With Seldom, we created inputs in English units, because if you go to NWIS Web, and most engineers are using English units, but if you needed the metric, you can get metric outputs. It'll transfer everything. Now, significant figures. The default is 3, because most environmental data are reported with about 3 significant figures. If you're worried about a certain output, you can go to 15, double precision, 15 digits. Now, I do not recommend that, the numbers that you get from Seldom are anywhere near that accurate. That's just so that you could copy results in a spreadsheet and, try and track down if a number looks weird. Or if you want to recreate the calculations we do outside of Seldom, let's say you were doing a model verification, you'd want those double precision numbers. If your main emphasis is TMDLs, when you round an annual flow, concentration, or load to an annual value, you round that to 3 places, the numbers aren't going to add up to as if you added up all the individual storms. They'll be within the rounding, but you're not going to get the exact same number. Things might round up or down. So, for TMDL, you might want to go to a higher number of significant figures, but, they're significant in terms of that's what's put out. But, with all the uncertainty in environmental data, very often, you're fooling yourself if you really think that you know that, phosphorus load in pounds per year out to, 4 or 5 or 15 digits. So then we just run Seldom. And I started groundwater modeling long ago. We used to run the models, groundwater models, for 24 hours and come back, and you'd hope and pray that you didn't make a mistake and have to run it again for 24 hours. So you can see Seldom runs fairly fast. All the calculations are done on the order of about a minute. Sometimes it's as short as a couple seconds. When you run in batch mode, it's not talking to you through the interface as much, so batch mode tends to run a lot quicker. Batch mode is when you've preloaded all the information you want to run, and then you can run a bunch of analyses together. So Seldom gives a number of output files depending on what you pick. So for all of them, you get this documentation file. So it's called your it compresses your analysis name. We called it Chapman's Brook Eco Water Quality Out. So the .out file gives you your information, and it gives you your water quality treatment for your BMP. It echoes, what Seldom version you used. It echoes all that information that you could have put in. It tells you about the project, the analysis, the site. Precipitation event file, that's PE. So that's -PE. The precipitation event is the duration, the volumes, the time between events for all the individual stations, and it breaks it down into annual load accounting years. So in annual load accounting years, as Seldom runs, it keeps track of the time between event midpoints, and when that gets to 365 days, and because I'm a nerd, every 4 years it gets to 366 days, and so it just lumps those storms together. Seldom's not running an actual history. It's not a time series. It's a series of randomly generated events that get lumped together into annual load accounting years. So the highway runoff water quality is -HQ. So if you want to look at the files, the highway runoff and BMP quality, you look at HQ. The upstream water quality is UQ. Dilution factors, which is the ratio of highway or urban runoff to the downstream flow. That's the dilution factor. We'll talk about that in a subsequent meeting. Our pre-storm stream flow file name. So that gives you your population of pre-storm flows that we used. The storm flows gives you the runoff coefficients, durations, volumes. The annual highway runoff file, that's what you'd use for the TMDL analysis. So that's the dash annual. And then our downstream runoff quality, if you're looking at the risk of exceeding water quality downstream of an outfall, that's DQ. All right. And so, Seldom gives you the information here, the path to these files, but you can also open your output file folder. Now, EPA wanted to make sure that people weren't going in after the fact and like monkeying to get the answer they want. So they asked us to create a specific, folder directory so that they could, kind of verify that the results are the results. So Seldom places files in a default place on a given computer. Once you create them, you can move them anywhere. But it creates a FHWA Seldom directory on your root drive. Most of us, that's the C drive. It creates a project. Here, I can come here. So these are all the projects. So this is like my filing cabinet. And then here's my drawer in the filing cabinet. So you can see that, let's see, we did the echo water quality. I was kind of playing around with this yesterday. So this is the analysis name, and it's truncated to get rid of spaces and special characters. So then for tracking, it gives you the output. So we ran this today. So if I make changes, or even if I don't make changes and run it tomorrow, it will show up as a different day. And then you get your runs. So if I was playing around with the analyses, it gives you your runs, and then you would know that, use the last run of the day if you were looking for documentary purposes. So if I click run, I get all these individual files. So again, I get our annual, our dilution factor, downstream, highway quality out, etc. So I've gone a little bit beyond the time you're invited. It looks like we've got most of the people still here. So I'll just quickly jump into the output, and then I'll let you go for the day. So, so here's our output file. Now, all the Seldom files, so that you can use them with different post processors, are tab delimited. Comments and information start with this pound symbol. Numbers are in tab delimited format. So this tells you about the Seldom version that you're using. This gives you where you ran that Seldom file from. I would suggest that if you're doing it like for an environmental impact statement or documentation, it might be best to run it in this FHWA Seldom directory, right in this root directory, FHWA-Seldom, just because then, where you run it gets put here. So if you have some silly file name, it will be put in the official output. Information about Seldom, the disclaimer. It talks about what an annual sequence. So you can see here's our analyst. It gives the role, initials. If I'd put in my complete address, cell phone number, everything, that would go in here. Here's the project information with the abstract, the GIS grid we used, the analysis information, the ecoregion we used, precipitation data set, streamflow data set, the highway site, upstream basin, and here's all the BMP treatment statistics. So it tells you what the pre-storm, so this is just the documentation file. To get into individual files, I'm just going to go to the ecoregion, the annual analysis. We'll dig a little bit deeper into the more detailed in the next class, but because this one's easier to look at. So again, we echo out a lot of the information that we put in. So it tells you about your plotting position, output. It gives you analysis information, your highway site information. Because this doesn't have any upstream or downstream information, it doesn't give you the highway site. It doesn't give you the information about the upstream basin. In all the Seldom outputs, you're going to get your variable names for the columns, and it will tell you what each thing is. And there you go. I was talking about this. It says, note the sum of annual fluxes and loads may not equal to the sum of individual storm values due to significant rounding. So this gives me information about total phosphorus from highway runoff. So here's my statistics that it used to generate the population. And let's see, this link isn't okay. So in this case, I put the reference in a location. This might be our data release, so this might not be available yet. I guess I could risk clicking on that. But the meat of the Seldom output are going to be these tab delimited tables. So in this case, the loads are in pounds, precipitation is inches, flows are in cubic feet, and normalized flows are in watershed inches. So here's the output. So I can copy this. If I go to my trusty spreadsheet here, I add a tab. So here's all the annual values. So the annual flows, that's cubic feet. Here's in watershed inches. So there's the precipitation, and that's the runoff generating precipitation. So let's say I want to see what my long-term average runoff coefficients are. I can do the precipitation in watershed inches divided by the highway runoff in watershed inches divided by the precipitation. And I can see that there's variation from year to year. And if I do I could take the long-term average. Hopefully it comes up to be like 70, yep, about 79, 80. Schuler would tell you that like the rational method and the Soil Conservation Service would tell you this should be 0.96, but if you look at actual research, pavement is not 100% impervious. You get, evaporation, transpiration, well, not transpiration, but you get absorption, water leaking, and infiltration through. So our statistics for many sites shows that a fully impervious surface has an average runoff coefficient of about 0.79-ish, and field studies show that yes, you lose 20 to 30% on an annual basis from pavement. Let's see what else. Okay, if we can look at our discharge flow in watershed inches. So if we divide that divided by the annual precipitation, and we do that, and we can see now Seldom has a different flow reduction. Well, we'll do this. Seldom has a different flow reduction for every storm, but we can see this median BMP. About 76% of the highway runoff passes through the BMP and discharges to the stream. So this is kind of like your median performance BMP. So that means it's reducing about 26% of the flow. All right, so you can do all kinds of examples like that. I'll do a quick example of, let's see, if you are going to become a Seldom modeler and use the output a lot, we've Federal Highway has specified this. It has had us develop this post processor called Interpret Seldom. So I'll just do a quick example. And what do we have? We did DOT simulation. So I'm picking my project. And now let's graph annual loads. And let's see. Oh, I must have picked the wrong one, but let's just pick Chromium. And there's the highway and BMP. And if I update the graph, and so this Interpret Seldom will give me a graph. Here's annual loads. I think this, I accidentally picked another analysis, but you know, you kind of get the idea here. You get your loads, you can do it in landscape, you can copy the graph, you can paste it into your PowerPoint, you can mess around with the graph formatting. And one thing that this program does for you is it does pull the data for you. So sometimes with some analyses, you kind of have to fish through some of the outputs to get what you want. With this Interpret Seldom program, it will grab stuff and format it for you. Whoop. Yep, I guess I didn't copy that successfully. Okay. Oh, something's. Oh, Excel is acting a little funny lately. Oh yeah. So not engendering a lot of confidence, am I? Okay, so that's copied and pasted. There we go. Because I had that other cell formatted, it didn't want to let me do what I wanted to do. All right, so that's a quick go through. This Interpret Seldom program does a lot of work for you. It makes things easy, but you do have to have your IT person at it. So that's why I said people who are going to do Seldom modeling may want to get it on their computer, or, you know, if your IT people are nice and supportive, then, you know, it's a pretty standard program. It's from a USGS server, so it's there. All right, so I've talked on a little bit longer than we had hoped, but hopefully we covered everything. At this point, are there any questions?
I thought it was good, Greg. It's kind of like drinking through a fire hose, but it was a very good introduction.
Oh, thank you. Yes, there's a lot of information. I try to focus on playing with the model instead of just death by PowerPoint. So hopefully, I guess the takeaway from today is if you can do online shopping, you can run Seldom. So, you know, knowing what to pick and whatnot, that comes along with a little more information.
I'm going to go ahead and stop the recording, Greg.
Yes, sir.